Here is the formula to calculate the future value of an annuity due with all of the variables listed. We're going to go through how to input this formula into Excel. As an example, let's say that someone deposits $3,000 at the beginning of each year for 4 years into an investment earning 7% compounded yearly. What is the future value of the annuity? One important note, to use this formula, the interest compounding periods must match the payment periods. For instance, yearly to yearly, semi-annually to semi-annually, or quarterly to quarterly. This is extremely important. So the variable n must match the number of payment periods per year. I've listed all the variables with their amounts, as you can see on the screen, so we can reference them when we enter the formula into a cell. We're going to put the answer in cell B9, so we left-click on cell B9 so it's highlighted. Next, we type in an equal sign. Then, following the formula, we left-click on the payment or deposit amount, cell B2. From here, we type in a multiplication sign, which is Shift-8 on the keyboard. Next, we type in 4 open parentheses, and then we type in a 1. From here, we type in an addition sign, then another open parentheses. Next, we need to left-click on the interest rate amount, cell B3. Then we type in a division sign, which is a / on the keyboard. Now we need to left-click on the number of deposit periods per year, cell B5. We always use the deposit periods. If the compounding periods do not match the deposit periods, then we have to adjust the interest rate, and we'll go through that in the next example. Next, we type in 2 closed parentheses to close off the r over n portion and the 1 plus r over n portion of the formula. From here, we need to type in the to a power symbol, called a caret sign, which is Shift-6 on the keyboard. Next, we type in an open parentheses, and then we need to left-click on the number of deposit or payment periods, cell B5. Then we type in a multiplication sign, and next we left-click on the number of years, cell B6. Now we type in 2 closed parentheses to close off the n times t portion and the 1 plus r over n raised to the n times t portion of the formula. From here, we type in a minus sign. Then we type in a 1, followed by a closed parentheses, which closes off the top part of the fraction in the formula. From here, we type in a division sign, a /, then type in an open parentheses. Next, we left-click on the rate, cell B3, then we type in a division sign. Now we left-click on the number of deposit periods, cell B5. Again, we use the number of deposit periods because, as you'll see in future examples where the deposit and compounding periods do not match, we need to get them to match by adjusting the interest rate. Then we type in 2 closed parentheses to close off the bottom part of the fraction. Next, we type in a multiplication sign, then another open parentheses. From here, we type in a 1, followed by an addition sign. And next, we left-click on the rate, cell B3, and then we type in a division sign. Now we need to left-click on the deposit periods, cell B5. Then we type in a closed parentheses to close off the formula. From here, we hit the Enter key, and we have our answer of $14,252.22 rounded off, which is the future value of the annuity. Now for an example where the deposit or payment periods do not match the compounding periods. Let's say this time that someone deposits $3,000 at the beginning of each year for 4 years into an investment earning 7%, but this time compounded quarterly. What is the future value of the annuity? The only thing that has changed from the previous example problem is that there are 4 compounding periods per year. So I'm going to list the variables with the amounts with that one change. As I stated earlier, to use the formula, the interest compounding periods must match the payment or deposit periods. To solve this problem, we need to convert the interest rate to the effective interest rate. So I'm going to add that variable to the list. Here is the formula to calculate the effective interest rate with all of the variables listed. We're going to enter this formula into cell B19. So we left-click on cell B19. Next, we type in an equal sign, followed by 2 open parentheses. From here, we type in a 1, followed by an addition sign, then another open parentheses. Next, following the formula, we left-click on the rate, cell B15. Then we type in a division sign, and then we left-click on the number of compounding periods per year, cell B16. From here, we type in 2 closed parentheses, followed by the to a power symbol, a caret sign, again Shift-6 on the keyboard. Now we left-click on the number of compounding periods, cell B16, and then we type in a closed parentheses, then a minus sign, and then the number 1. From here, we hit the enter key, and we have our answer of 0.071859. And now we're ready to enter the formula, which I've done already. The only difference from the first example is that we're using the effective interest rate in place of the annual interest rate. So the formula is written exactly the same with only that difference. I'll hit the enter key, and we have our answer of $14,316.33 rounded off. You can see that this value is greater than the first example, and that is because of the extra compounding periods. In both of the previous examples, the deposit periods were yearly. So we're going to do one more example, and this time the deposit periods will not be yearly. This time someone deposits $500 at the beginning of each month, again for 4 years. The yearly rate is 7% and is compounded quarterly. What is the future value of the annuity? So we have monthly deposits and quarterly compounding. To do this, we have to first convert the interest rate to the effective yearly rate, then second, convert it to the nominal rate. Here again is the formula to convert it to the effective rate. And here's the formula to convert the effective rate to the nominal rate. I put in the formula for the effective rate in cell F7, as you see on the screen. It's the same formula as the last problem. I'll hit the enter key, and we get the same value as the last example. Now we need to input the formula for the nominal rate. We're going to enter this formula into cell F8, so left-click on cell F8. Next, we type in an equals sign. Then we need to left-click on the number of compounding periods we need to be at, which is F5. The number of deposit or payment periods, not cell F4. Next, we type in a multiplication sign. From here, we type in 3 open parentheses. Then, following the formula, we type in a 1, then type in an addition sign. Next, we need to left-click on the effective interest rate, cell F7. And then we type in a closed parentheses to close off the 1 plus effective rate portion of the formula. From here, we type in a caret symbol, or the power symbol, Shift 6 on the keyboard, and then we type in an open parentheses. Next, we type in a 1, followed by a division sign, and then we need to left-click on the number of compounding periods we need to be at, which again is cell F5, not cell F4, because we need the compounding periods to match the deposit periods. Next, we type in 2 closed parentheses, followed by a minus sign, and then we type in a 1, then we type in a closed parentheses to close off the formula. From here, I'll hit the enter key, and we have our answer of 0.06959591 as the nominal rate. And now we're ready to enter the formula, which I've already done. The only difference from the previous example is that we're using the nominal interest rate that we calculated from the effective interest rate in place of the annual interest rate. So the formula is written the exact same way with only that difference. I'll hit the enter key, and we have our answer of $27,741.83 rounded off. And there are actually different ways to calculate problems like these, but I have found this to be the most useful. Alright my friends, hopefully you got something out of this video. I do have more videos right there for you. Till next time, I am out of here.